Hi, everyone. Now that we know more in regards to what the different levels of organization and what it means to be a living organism, in in this video, we'll talk more about the first two levels of organization, which kind of gives ideas behind the initial components that help the cell form, which brings us to the idea of the chemistry of life. So, in the atomic level, there are the basic functional unit is called an atom. And what atoms are is that they are composed with different subatomic particles, including protons, neutrons, and electrons. Protons are positively charged, neutrons are neutral, electrons are negatively charged. Protons and neutrons are specifically located in the nucleus, and the electrons are found in the orbitals surrounding that nucleus itself. So, another form of technology that we want to understand is called elements. These are pure substances that contain only one type of atom. And there are 92 naturally occurring elements, but only about 25 of them are found in living organisms. And 6 elements in this group basically composes 99% of the atoms that you see in actual living organisms. And these include oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. And one thing about these elements is that there can be different forms of them, and these are called isotopes. They are naturally occurring atoms with the same number of protons, but different number of neutrons than the normal version of that element. And these additional neutrons can make some of these atoms very unstable. And if they are unstable, they to get to a more stable state, what many of these isotopes do is release a bit of tiny energetic particles from their nuclei, and these emissions from the nuclei is what is known as radiation. So, for example, if we have carbon 12, which is our normal version of the element, that's stable, it's non-reactive, it has 6 protons, it has 6 neutrons. But then if we look at like carbon 14, which has 6 protons and 8 neutrons, now it's like all unstable, and it's like a washing machine that is overloaded with like soap and like everything else. It's like a whole mess. So, radioactivity in general is basically the gradual disintegration of unstable atoms that releases subatomic particles and energy in the form of basically radioactivity. So, what happens is that there are like 4 different versions of radiation. The first one being alpha radiation, which is very slow moving and can be stopped by like paper or skin. But if you ingest it, it's basically hazardous. Then there's beta radiation, where it is more faster than alpha radiation, but it can be stopped by like glass or like aluminum foil, concrete, that kind of thing. Oh, no, not concrete, foil or glass, basically, like this. And it's hazardous when it's ingested, just like alpha radiation. Now, the next level of radiation is called gamma radiation, where it's like light speed and it can only be stopped by like concrete, lead, or steel. This can damage your skin and your internal organs. So be very mindful if you guys ever work with like radioactivity and so on. And then we have neutron radiation. This is basically what happens when you have a nuclear fission occur. It can travel through air, it can damage skin and internal organs, basically so much damage that it can be uh, irreversible. So one thing that is basically need to be known is the amount of like radiation exposure in the US. This is half of it's like natural, others are more medical, and then there's like nuclear medicine, stuff like that, and different consumer products. Some applications include diagnostic radiation, like um, MRIs, some therapeutic radiation. There are some like parts of nuclear medicine that actually help in like curing different um, diseases. And then there's like radiometric dating where you look at a set of fossils and you can tell, or a skeleton, and tell when they're actually from. So now to avoid these um, different elements and atoms from being so nuclear in terms of like radiation, what they do is a form of chemical bonding. And this is basically depending on the reactivity of the atom itself, where it's determined by the electrons in the outermost shell, which is called the valence electron shell. And what we see is that with the atoms that have full valence electron shells, they are non-reactive, like the atom or element of neon. It's a happy, stable, non-reactive element. Now, if there are like partly full, it can interact with other atoms through a process called chemical bonding to form different molecules. In this case, the example would be oxygen, where it has 8 or 6 in the outer shell, but it needs more to be complete. So when we look at different bonds, it can be single, it can be double, it can be triple, depending on the number of valence electrons that are available. So for example, carbon has 4 valence electrons, so it can make up to 4 bonds with other atoms. And now there are a couple of other terminology that we need to know and keep in mind as we go out throughout this course. So atoms can form molecules, where molecules refer to two or more chemically joined, uh, 2 or more atoms chemically joined by covalent bonds. These can be same or different elements. So some examples are like these, where it's like hydrogen, water, NH3. Like these have similar ones or different ones. But then when we look at a compound, it's always different elements. So it's like 2 or more of the different elements being joined by either covalent bonds or ionic bonds, and we will talk about those in a few. So covalent bonds are bonds between two sets where they are sharing electrons. Now there are 2 types of um, covalent bonds, where the first one here is saying that it is covalent, where nonpolar covalent, where it's basically shared equally and the bond itself is symmetrical. And then there is another set called polar covalent. These are shared unequally because one atom in that molecule is more electronegative, and the highly electronegative one, like this water molecule here, what happens is that the electrons get held to that oxygen more than the others, giving like a partial negative and a partial positive kind of charge. The lower electronegativity atom will end up with a partial positive. So essentially what happens is that this bond becomes asymmetrical. It's like the oxygen and the hydrogen are trying to like they're sharing it, but it's unequally shared between them. So like these two fighting over the electron, basically. So now what happens is when there are uh, certain differences in electronegativity, what happens is that they end up with a net charge. And what happens is with atoms, what happen is so in terms of charge, atoms normally have no net charge. So the number of protons equal number of electrons. But when we have ions end up forming, the electrons are not shared. They are completely transferred. So when a valence electron is donated or accepted between the different atoms to kind of fill their outermost shell, what happens is that they end up ending up with a charge, and this ion formation. So an ion is basically an atom that ends up with a charge. So basically a cation is one that loses an electron and becomes positively charged. It's like I lost an electron and it becomes positive. So in this case, what we have is like sodium plus. When you see that, you just say that, okay, so in this case, sodium lost an electron. Or like in this case, where magnesium 2 plus, what happens is that magnesium itself lost 2 electrons. Now, when we say it's an anion, it's basically an atom that gained an electron, where it becomes negatively charged. And what happens there is that if we have chlorine with a negative sign next to it, that's basically saying that there is a chlorine atom and it gained an electron. So now what happens is with ionic bonds is that these are like the charges themselves end up being like opposites attract. So it's basically saying that it can form a bond between any two oppositely charged ions. So like a cation will be attracted to an anion. And these will be more attracted to each other because of the electrostatic forces in front of them. And essentially, these ionic bonds can be easily disrupted in the presence of like polar molecules. In this case, it could be like water, like salt and water, where the ions get pulled apart. And as the water evaporates, you end up with sodium and chloride ions forming ionic bonds again. So they can be separated but pulled back together again. So now what actually determines the type of bond that ends up occurring between a molecule? So pure covalent bonds or non-polar covalent bonds, all of this just depends on the electronegativity of an atom. This is basically the tendency of an atom to attract a pair of bonding electrons to itself. And the type of bond itself depends on the difference between the atoms itself with the electronegativity. So if it's like between 0 and 0.4, those are covalent bonds that are nonpolar and the electrons are shared equally. And then when we have polar covalent bonds, what happens is that the electrons end up being shared unequally, where you have the electronegativity difference of 0.4 and 2. And then anything above 2 would be your ionic bonds, where they are actually completely transferred. So if we have higher than electronegativity, the more strongly electrons are attracted to it. So um, it it all depends. So if a question comes up like if you have this like 2.5 electronegativity difference, what type of bond it would be, and your answer for a 2.5 electronegativity difference would be ionic bond. So now we get to talk more about an item called electrolytes, and these are um, any substance that can be ionized in water and conducts electricity when it's in a solution form. So in this case, most electrolytes are very critical for your body's functioning. That way it's like a keeping everything moving. And we'll talk more about like some of these later on when we talk about like respiration and stuff like that. So now, one of our favorite solvents in life is water. So just to kind of recap on things where it's definition wise, where a solution is basically a liquid that is a homogeneous mixture of substances. There are no clumps involved. So this is like a solution where everything's mixed together. The solvent itself is the dissolving agent of whatever yours want to dissolve. There's the solute. In this case, it could be like sugar being the solute and water being the solvent. So now you have sugar water as the solution. So an aqueous solution is specifically when uh, uh, water is the solvent in this case. So now when we think about water, the molecules themselves are very tiny, asymmetric because it's an uh, polar molecule because the oxygen has more electronegativity to it. With these properties, what happens is that it allows it to kind of interact easily with other polar molecules. And in this case, it allows it to form hydrogen bonds. So it's like the oxygen of one water molecule can interact with the hydrogen of another molecule, forming like a little tiny bond between them to kind of keep them more together. And um, basically what happens is that the partial negative charges and the partial positive charges end up getting attracted to each other. But there is no electron sharing or transferring involved when it comes to hydrogen bonds. So one other thing that we think about when it comes to water is that there is the aqueous solutions in like hydration shells, where we have ions in like these protein solutions, where when we look at like electrostatic situations between the water and the ion result, like basically breaking the bond between them, but then basically orienting them in the direction of which partial charge they have towards the, so with the negative charge of the um chloride ions, what happens is the part of the oxygen that is positive, partially positive, ends up going towards the negative charge. And this kind of shows like with proteins as well, where if you have like polar ones on the outside, it interacts with all the outside like water and stuff like that, but then the inner ones are more non-polar, where it attracts more of like the hydrophobic, where it's like not as water friendly. I'll fix this when I put the presentation up. So, for example, if a student dissolves some table salt into a glass of water, as the water molecule interact with the sodium ions and the chloride ions, the atoms in the water will be oriented so that these are a couple of your choices. Take a moment to think about this, and then the answer to this is specifically that it is the oxygen itself is of the water will be nearest to the sodium ion, and this is because the sodium ion being positive, it's facing the partially negative oxygen in the water molecule. Now, just to kind of keep some more definitions in mind, where we have uh, terms like hydrophilic and hydrophobic. These are varying in whether they like water or not. So hydrophilic is water loving. So when we look at that, it's basically ions and polar molecules that stay in solution because of their interaction with the water's partial charges, such as like sugar, salt, so on. It stays dissolved. But then when we put like hydrophobic or water disliking or hating or fearing, what happens is that these molecules remain mainly non-polar, that they do not want to mix with water, basically. So like oil and water, this is why that they're separating out every time into different layers. And then with colloids, these are substances that form stable suspensions of fine particles within like a liquid, where it's like cornstarch like this. So now why do we not like, why is it like oil and water not wanting to mix together? So oils are mainly uncharged and nonpolar molecules. So when we put it into water, it ends up forming like this hydration shell, where it's like trying to protect itself kind of thing. So it's like it kind of pushes the oils together, it pushes the waters together, and just like tries to, it cannot bind because there are no charges that can attract the uh oils. And basically, since it's a non-polar substance, it ends up pushing it away, that it doesn't have any charges that it can attract each other with hydrogen bonds. So a couple of properties of water includes adhesion, uh, cohesion and surface tension, and a couple of more, which we'll talk about in a little bit. But first, let's talk about adhesion. Adhesion is when water molecules form hydrogen bonds with other substances. So when we look at this here, adhesion is like a water on a leaf, or like water on something plastic, stuff like that. When it's cohesion, what happens is it's basically like two water molecules holding hands. It's like water molecules forming hydrogen bonds with each other. And then what happens with like the high surface tension itself is the fact that when we have air and water meeting each other, what happens is that the water molecules bind tightly to a point where uh, bind more tightly than air molecules at the surface around it. So it kind of comes together more tightly. So these kind of come along when we look at like capillary reaction, where these molecules come together and through narrow spaces. So like going up from the roots to the treetops, it's like going up and pulled along a polar surface when cohesion is actually stronger than adhesion. So what happens is the water molecules or any kind of liquid that is allowed, it kind of goes up. And if it's a thinner diameter, what happens is it goes faster up that um surface that is like pulling it up basically. So now one other property of water is that water is actually denser than l- uh, denser as a liquid than a solid, because what happens is that water itself expands when it goes from liquid to solid. So that's why ice ends up floating on liquid. But when the temperature drops, what happens is that they start to move more slowly, and the hydrogen bonds between them become more stable. So when water freezes, it becomes more of like a lattice structure where it's like more defined with more space in between, that it's like a, this structure here. But when it's like not as liquid, it becomes more closer together and like all that. But one thing about that is that ice can actually insulate the liquid water in below. So that's how we have some organisms that can survive during freezing temperatures. Another property of water is that it has a high specific heat, where the temperature itself uh, is kind of requiring a large amount of heat energy to increase the amount that the temperature is in, by 1 degree. So like the amount of hydrogen bonds that occur in the water molecules, it ends up taking so much energy that we can't uh, 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 to kind of shift it up by a degree. So this is why when the temperatures around like large bodies of water is more stable, because it ends up absorbing or releasing a lot of heat without great changes to the overall temperature. So like the climate near the shore is more cooler than when you go inland, because the cool ocean breezes end up uh, uh, cooling it down compared to areas that are further in. Now, another thing to think about is that water has a high heat of vaporization, and this means that when heat energy is transferred into liquid, water molecules as kinetic energy, which kind of increases that movement and then makes it easier to kind of break the hydrogen bonds between the water molecules. And this kind of, the high energy water molecules ends up escaping the surface like vapor. So like that's what's happening when you're uh, boiling like water and stuff like that. So like when when we like do a workout or stuff like that, many different organisms like us, we sweat to cool down because the body, when heat is transferred to like water molecules in sweat on our skin surface, the water molecules break away and end up evaporating from the skin, allowing us to kind of cool down. So now another property that is not included in the main sets of properties that we just talked about is basically the dissociation of water. It can go through a spontaneous reversible dissociation where water ends up hydrogen and hydroxide ions, but the protons cannot exist by themselves. So they dissociate into dissociate and associate with a water molecule to form basically a hydronium ion. So it kind of goes back and forth like this. So in pure water, like that we like have, the concentration of hydrogen ions and hydroxide ions are equal. When it goes more acidic, like lemon juice, it has more hydrogen ions than hydroxide ions. And when it's basic, like ammonia glass cleaner or something like that, what happens is that that solution has more hydroxide ions than hydrogen ions. So what we end up seeing or trying to figure out what is actually happening, we have a scale called the pH scale. And in this case, it is in the amount of hydrogen ions. It's the basically the log of the concentration of hydrogen ions when you go from 0 to 14. If you have uh, more hydrogen ions, what happens is that you have a smaller pH, which means you're anything from like 0 to 6 is on the acidic side, where 0 and 1 have like the most acidity or more hydrogen ions than hydroxide ions. And then anything after 7 from like 8 to 14 has more hydroxide ions more than um, hydrogen ions. So like if there's like a question where it's like a battery had it, battery acid had more, um, uh, it would be like battery acid having more hydrogen ions than like milk of magnesia. So just keep in mind like the scale of it itself. So now one happens is when we have a certain pH, if it goes in any direction, in like too acidic or too basic, what happens is that they have uh issues in which they cause death. So what happens is that this needs to be regulated, and the main ways to regulate this is through some biochemical pathways that we have in our systems. And because if we do it, if it doesn't regulate it properly, it ends up going into more dysregulation, and that is no good whatsoever. So we have three sets of pathways that can be used. The first one is the chemical buffers like bicarbonate pathway, where it absorbs and releases different hydrogen ions into the solution. That way it kind of balances out in the amount of hydrogen ions. Then there are respiratory mechanisms where it kind of regulates between the CO2 and bicarbonate um, um, molecules. And then we have other renal mechanisms that kind of absorb and secrete hydrogen ions as we kind of need it. So now one of our favorite elements or atoms in life basically is carbon. It's the most versatile one that we can see because it has 4 valence electrons and it can form a limitless amount of molecular shapes with different carbons and other atoms. And what we see is with these different combinations, what we see is we can actually form like double bonds, triple bonds, single bonds, all those different types, making a different variety of compounds and molecules. So the formation of these carbon-carbon bonds was very important because we kind of understood how like different organic substances existed and like different inorganic ones depending on the amount of carbon that there existed. So now when we look at different molecules, what happens is that there can be different functional groups. So functional groups are basically attached to different carbon atoms like this group here, where like a carbon skeleton, and then we have a functional group that has some properties that make it either polar or non-polar. And some of these polar ones include amino groups, carboxyl groups, carbonyl groups. With amino groups, it's like NH2, NH3, those like an amino group. And then carboxyl groups are one with a C uh, carbon with 2 oxygens and a hydrogen, or C C with carbon with 2 oxygens and a negative charge when it's ionized. And then carbonyl groups are usually trying to link molecules like aldehydes at the end of a molecule or ketones like these. And then we have some other polar functional groups that are hydroxyl groups, where they act as like weak acids, where they donate hydrogen ions in a solution, where these are like this, like an OH group basically. And then we have phosphate groups, which are phosphorus and 4 oxygens together. So keep in mind with these because they also are part of like nucleic acids and acts as a good buffer to uh, different molecules and different systems. Then we have sulfhydryl groups, which are basically linked together via covalent bonds, covalent disulfide bonds specifically. So that just means that it has 2 sulfurs, and it's very common within like proteins. Now we have our non-polar functional groups. This is kind of the last set of it, and these are primarily just methyl groups, where they are highly stable, they are non-reactive, they do not form any hydrogen bonds because they are no highly electronegative um, components in it, and they are very hydrophobic. So if we have this, it's not going to mix with water. So in any case, it doesn't have to be just one functional group. It can be many more, like this amino acid here, where it has like a carboxyl group, it has an amino group, it has a hydroxyl group, it has a methyl group, and so on. So this kind of concludes our um, talk on chemistry of life. In the next video, we will be talking more in regards to macromolecules that we need in life. Awesome.